Alright, silly people, here's the situation. We are meant to calculate the percent error um, whenever you use this version of the Stirling approximation versus this one. Um, so the first one is a pretty good approximation and really starts to work really well whenever n is large. Um, the second one is a better approximation overall, but has an additional term which will take up more computation time and therefore um, is useful to neglect sometimes. The difference is the 1/2 natural log 2 pi n term there. Um, so to calculate the percent difference, you want to do the value of the first approximation minus the value of the second approximation divided by the value of the second approximation. So we're talking about doing natural log n times n minus n uh, minus and that better be a absolute value as well. Um, 1/2 natural log 2 pi n plus n ln n minus n. That's the numerator, and then the denominator is just that same stuff. So n ln n minus n plus 1/2 ln 2 pi n. You do get a little bit of cancellation. The n ln minus n stuff on the top cancels out. So rewriting it now, you'll just have 1/2 ln 2 pi n on top. It's an absolute value. The minus sign will go away. And then on the bottom, you're talking about n ln n minus n plus 1/2 ln 2 pi n still. So that's the percent error as a function of n. If you want to plug those in to check for like n is equal to 10, you'll get something like 0.137. So pretty big error, all things considered. A 13.7% error in the approximation. But once you make n larger, you're talking about percent error for n is equal to 100. You get something like 0.008 instead, 0.009 actually. So by just increasing it by an order of magnitude, you've gone down to less than 1% of a difference. And then whenever you increase order of magnitude again, you get something even smaller. Now it's 0.0007. So even smaller of an error. And so when you're doing things in the field of statistical mechanics, and you're doing things on the order of 10 to the 23, the error really becomes quite small. And so the difference term, the 1/2 ln 2 pi n, really doesn't make a difference when you get to those big magnitudes. Okay?